We're going to use the summation notation to calculate the area under that log x curve. So it tells us that we're going to use a left-hand Riemann sum. Our interval width is going to be 1, or delta x is going to be 1. And we're going to approximate the area under the log x function from 1 to 4. So if the delta x is 1, that means that our n is going to be equal to 3. So using this summation notation, we're going to first of all find the area underneath the first term. Okay, so the area underneath the first term is going to be, well, the height at, we're going to use the left edge height. So the left edge height in this case is going to be 0. And we're going to have a interval width of 1. And so that area is going to be 0. So the next interval is going to look like this. I'm just going to draw it in first. So there's our left edge for the next interval, and then the left edge for the last interval is going to be right here. Just draw that in again. So that's going to be our left edge height. And so there's our 3 rectangles that we're going to calculate. Okay, so the first term is going to be, we'll take the height. In this case, it's going to be 0. Okay, so that's going to be the height for the first term. And then we need to multiply by that interval, the interval width, which is going to be the delta x, which is the interval width divided by n. In this case, it's going to be equal to 1 plus the height when, in this case, the next term is going to be at 1 plus the interval width, which is 2. So the height at 2 is going to be log 2 plus or times the interval width, which is 1 plus the height at when n is equal to 3. So in this case here, we're going to have the height, it's going to be at log 3. And the interval width again is going to be 1. Okay, so then summing this all up, we're going to end up with 0 plus log 2 plus log 3. That becomes log 6. And then we can calculate that area to be approximately 1.79. Okay, and that's going to represent this area, which I've shaded in green underneath the log function. Riemann sums allow us to approximate areas under curves by using rectangular areas. This is very useful for finding areas under functions where we don't really know what the antiderivative is. We can use this for all other areas as well, though. So the common ways to apply Riemann sums are as left-hand Riemann sums, which I've kind of highlighted in green, where the left edge of the rectangle is going to touch the curve, and that's going to establish the height of the rectangle on the left edge. Okay, there's right-hand Riemann sums, where the right edge of the rectangle touches a curve, and the right edge then establishes the height of the rectangle. And then there's the midpoint, so where we use the middle of the curve, where the rectangle will touch the middle of the curve to establish the height of the rectangle. Okay, so there's left hand, right hand, and midpoint Riemann sums. Now we've come across this summation notation where the area under that curve we can use by using this formula. And basically how the formula works is that we start with f of a, and so that establishes the height. So I'm just going to highlight what I'm talking about here. That expression is going to establish the height of the rectangle, and this is the width of the rectangle. So that is the interval width, which is I, where we calculate with b minus a, and if we divide it by n, the number of intervals, it gives us the width of the interval. So essentially that is going to give us the delta x terms that we're looking for. Okay. The inside of that f expression is just how we go from each rectangle. So we start at a, and ik over n, well, I over n represents the interval width. That k just establishes how many terms over we are. So for example, when k is equal to 1, we're going to start at a. So starting at a, we're going to start at a, and we're going to move over one k value, which gives us the height at this coordinate here. So we're just going to add one interval width and get the height at that point. So this expression essentially is going to calculate this right-hand Riemann sum. And when k is 2, we're just going to use the height at this position where we're 2 intervals over from the starting point of a. And so that sigma notation is just a way to generate each term or each rectangle of that Riemann sum.